Hello guys, welcome to our channel, The Fishing Road. In this case, I will present you a practical method to select the typical capacitors that are used to start the single-phase induction motors and also to improve their rotation and to increase the torque of these motors. To be honest, I've seen a lot of information through the web and through other videos, but none of them or the recommendations that I found, none of them have worked to be. It's for that I hope that you find interesting the proposal I made for you. See you next video.
So let's start with the equivalent scheme of a single-phase induction motor. So then we will focus on how to select this working capacitor. So as we will use a washing machine motor, then the scheme of this washing machine induction motor, then the motor will have 4 windings. The one winding is devoted to the spin with a high speed rotation, and another auxiliary winding just for starting, and then 2 more windings for low speeds for the washing purposes. The one is devoted to clockwise rotation, the other one is a counterclockwise rotation. It will depend on where the capacitor will be connected, to one winding or to another winding. So let's think that we have the old motor. This motor is coming from an old washing machine, and we are thinking to use in any of our projects. Maybe if this is a motor like this, we find that there is a lot of connections, but we don't know which connection correspond, which one winding or line, etc. The same with the capacitor. Maybe there is no information with the plate. Maybe we don't have the old capacitor that was installed in the washing machine. So what can I do to select a proper capacitor value? To be honest, I found a lot of information in the webs and also in some other YouTube videos, but the recommendation that I found there never worked to me. Sometimes you can see, okay, use the proportion of 70 microfarads per kilowatt, or you can also calculate the proper capacitor that so the power factor goes to 1, or sometimes there are formulas where you can calculate the capacitor based on the power of the motor, the voltage that is applied, and the power factor of the motor. But once I've used all these recommendations, never worked. The values I got was so far from the capacitor that the motor really needs. Then I will present to you the method I use to calculate the proper value. So I hope this method can be useful for you, and after a very short technical presentation we will go into this method. Let's go. So maybe the first thing we should ask ourselves is, why do we need a capacitor? Think about one stator and one rotor. The stator has two windings, one winding with two coils, and depending of the incoming current, depending the direction, there is a magnetic flux that produce in rotor an induction with a magnetic field that is pulsatory, goes from one direction to another direction, but it doesn't produce any any movement at all. Let's try to add a second winding, the green one, that to make things different is set off 90 degrees, 90 mechanical degrees, and then if we see the adding of one magnetic field and the other magnetic field, the result is another pulsatory field that is about 45 degrees, something like that, but there is no movement at all. Let's go one step forward. Now, instead of feeding the two windings with the same voltage, in this case we will apply to the green winding, we will apply a voltage that is delay 90 electrical degrees from the red one. In this case, this 90 degrees corresponds to about 4 milliseconds in 60 Hertz. Then the resulting field that is produced by the green and red results in not a pulsatory magnetic field, but in a rotationary magnetic field, because when the green is rising, the red magnetic field is dropping, so at the end the sum of the two magnetic fields results in a rotationary magnetic field. So it results in an induction on the rotor that makes it to rotate, in this case in one direction, counterclockwise. How to produce a delayed 90 degrees voltage? It's so simple, just adding a capacitor to the green one. What happens if we change the position of the capacitor and now we install the capacitor, so the voltage applied to the red winding is in this case 90 degrees delayed from the green one. The result is the same. The adding of these two magnetic fields results in rotational magnetic field, in this case clockwise, so the capacitor can be permanently installed and then we will have the same torque. Then coming back to our washing machine engine, it's clear that should two different speeds are needed, then we will have 4 windings, 2 windings for the running and starting for spin, and the other 2 windings for the washing functionality. In the past, apart from the permanent capacitor, they were another capacitor for starting to produce, to give more torque, but it is no longer used. So if we focus on the washing functionality, the 2 windings are working the same way. If we feed one winding with the voltage line and install the capacitor in the other one, then the motor starts in one direction. The same if we feed directly the other winding and install the capacitor in the previous one, the rotor will run in another direction. So to do that, the only way is that the 2 coils, B1 and B2, should be the same. I'm sorry, but the criteria is now to make the power factor close to 1. Of course, the capacitor will help, but the distribution of voltages will not be good. Then what is the method we propose to select the capacitor? It's clear that the capacitor, the value of the capacitor should be so high that the motor can start with enough starting torque. But the higher the capacitor value is, the higher voltages are applied to the capacitor and also to the winding that is working for starting. So the idea is that the 2 windings should be support the voltage line even when they are working as a running winding or as a starting winding. This is the way the motor will run the best. If the capacitor value is too high, then the voltages could be higher. Is for that the capacitors normally stands for 450 volts. The normal operation is about 350. Then what we are going to do is to connect the terminals of the motor as the way they should be, from the line directly to one winding and to the first terminal of the capacitor, and then the other terminal of the capacitor should be connected to the other winding. We are going to take measurements of the voltage value at capacitor and the voltage value at the winding, starting winding, and we will write down, depending on the capacitor value we will use in each case, the capacitor value that will make the starting coil about 220, the line voltage. This should be the capacitor we have to select. In my case, I used to start with a value about 16 microfarads. These single-phase motors from 100 watts to 1 kilowatt. Capacitor values ranges from 3 microfarads to no more than 40 microfarads. So with some capacitors you can find very cheap, about $5 in internet or in electronic shop, and making serial and parallel connections, you can you can place a lot of capacitor values, and I think that with this practical method it would be easy to find and to select the capacitor instead of making calculations and very hard formulas. There is an additional video where it is explained based on measurements of voltages and currents through all windings, how to draw the full phasors, voltage phasors, and then it is explained how these capacitors and windings can reach very high voltages. Let's start with a capacitor value of 16 microfarads, and then we will take measurements of the capacitor between the voltage line and the terminal of the capacitor and the neutral.
Pues vamos allá. Sonido es un poquito bronco, eso quiere decir que está un poquito por encima de los valores nominales. En este caso la bobina está a 327 voltios. Está por encima, lo tengo aquí amarrado, está por encima de valores nominales, y contra la fase el condensador está a 297 voltios. Bueno, pues vamos a probar.
Okay, let's then try with another capacity value. As you can see, in this case 327 volts for the winding voltage is too high, so 16 microfarads is a little bit high. After disconnecting the capacitor, be careful because it can be charged depending on the voltage that was present at the time it was disconnected, so be careful. Here we have several capacitors, the 16 microfarads, 20, 3 and 4 microfarads. We've seen that 16 is not adequate because voltages are too high, so then we will not try the 21. We will start with the 4 microfarads capacitor.
Ya el motor es mucho más, perdón, el sonido es mucho más normal, no vibra tanto. Si conectamos contra el neutro, vemos que la bobina está a 99 voltios, es decir, del orden de los 100 voltios. Y vamos a ver el condensador. que sería tensión contra la fase. ...254 voltios. Entonces vamos viendo que,
as you can see, with a lower value of a capacitor, the voltage of the winding is reduced from 327 to 100. There is not overflux at all, and it's for that the sound of the engine is quite smooth. But still there's still room to improve, because the first coil is at 220, the line voltage, but the starting coil is running at 100, and we can still place a higher capacitor. Here we have the 4 microfarads capacitor and the 3 microfarads. So the next value we can reach is 7 microfarads by paralleling the 2 capacitors. As you know, when you parallel, if you connect in parallel 2 capacitors, the total capacity is the addition of the 2 single capacities. So then we connect the terminals in parallel, and then still we have a free connection to take measurements. There is a common connection, and there is the connection where we can connect the capacitor and take measurements.
¿Qué valores obtenemos? Vemos entre el condensador y la fase 296. Hemos vuelto a subir la tensión del condensador 296 voltios, que es una tensión correcta, y la medida de la tensión de la bobina, que hemos dicho que era el punto del condensador contra el azul, que es el neutro, 165. Luego aquí tenemos que con 7 microfaradios llegamos a 165 voltios.
So we have improved, but there is still room to improve a little bit more. The next value that we can reach is, instead of paralleling the 2 capacitors, connect them in serial connection. We have the 16 capacitor value and the 20 capacitor value. So if we connect in serial these 2 capacitors, the resulting capacity is then the proportion of the 2 values multiplied and divided by the sum of the 2 values. So around 8.8 microfarads. So then we have still free connections to connect to the voltage line, to the winding, and also to take measurements.
¿Qué medidas nos da? Sigue teniendo un ruido bastante normal. No tengo ahora mismo aquí ningún cocodrilo para poder conectar bien contra la fase 314, que sería lo que mide la tensión del condensador. La hemos subido a 314 voltios y si medimos contra la fase 214 voltios.
Then it seems that we have reached the desired combination. Both windings are around 220, the line voltage. In this case, the starting is about 214, and the capacitor is also working within its nominal values. From 300 to 350 is a very nice voltage for the capacitor. Let's write down the resulting capacity after connecting in serial the two capacitors. So then a capacitor about 8.8, 9 microfarads, even 10 microfarads is the proper capacitor for this motor. Let's take some measurement about the final capacity. The real capacity of this serial connection is 9.1.